I won't be that long. It's like 15 minutes. Just quick disclaimer, I'm not soliciting any investments with this talk. All right. So I'm going to be talking about this paper that I love called the mode tree. And it's a tool for visualization of non-parametric density features. That might sound scary. It's not. I'm not going to assume any math other than that you've seen a histogram before. Because really this is about fancy histograms. So it's by these two guys, these two statisticians, Minot and Scott, from 1993. And I would say I'm going to say it's an inconsequential paper. I love it, and I'm going to present it, and it's got a lot of interesting things in it, but I've never seen anybody actually use a mode tree in my life. But maybe this talk will make it catch and it'll go viral. All right. So the problem that it tries to solve is this one of understanding the shape of your data. So this happens all the time. We measure something, and we get a bunch of values. So I hope everybody can see that. I'll restart that. All right, we get a bunch of values, and we want to plot it. We want to understand the shape of it. So maybe we make a histogram. So here's a histogram of this data. It's arguably the worst possible histogram. I've got one bucket of size 30, and all of my data falls into it, and we've learned pretty much nothing. So what went wrong here? Picked too big of a bucket size, and the bucket size is one of the parameters that we choose when we're visualizing our data. So this is too big. Let's use a smaller bucket size. Here we're using a bucket size of 10, and we get this visual of our data. And this seems interesting. Most of our data is in the middle, centered around 15. We've got these 3 buckets, but I made 2 choices here. Not only did I choose the bucket width that I want to use, I also chose to have the buckets start at 0. I could have had the buckets be centered, the first bucket be centered at 0, in which case I would have gotten this, a different visual that looks like the data is concentrated in a different place. So it's sensitive not just to the bucket size, but also to the starting point of the buckets. And we get a different sense for where the data is concentrated. And we're going to be talking about this thing called the mode, which is really where the data is most concentrated. And sometimes we will say that something is multimodal if we think that there are different places where it's concentrated and different local maxima in the histogram. So here we have this bucket size of 10. We started shrinking the bucket sizes. Things got better than that initial histogram. So let's shrink them some more, and we get this histogram. Now, I generated this data. It's synthetic data, and I happen to know that it came from a mixture of 3 normal distributions. So the fact that we've got 3 local maxima here is good, but we couldn't really know that a priori. And we've been shrinking the bucket sizes. We can keep smaller bucket sizes are better. Let's keep going. And we end up with something that's arguably tied for being the worst possible histogram, where each bucket just contains 1 value. So we've gotten different perspectives on the data as we've changed the bucket size. What's the right bucket size is an important question. And there actually is an answer if you make certain assumptions, and it's credited to Scott, one of the authors of this paper, who has spent his life thinking about histograms way more than anybody else. And there is actually an optimal bucket size to use if you assume that your data comes from a normal distribution, but I'm not going to get into that. But what the mode tree is going to try to do is it's going to give us a sense for where the data is centered, and it's going to give us a view into all the possible modes that we would get for all possible histogram bucket sizes. All right, so get ready. All right. So the first thing that we're going to do in order to get to that is we're going to look at a slightly fancier version of a histogram. which is this thing called a kernel density estimate. This is the only math that I will show. You don't need to understand all the math, but the basic idea is we're going to make a little normal distribution that is, and we're going to put a little normal distribution around every one of our observations. So the normal distribution is, it's called the kernel. That's why this function k. It's going to be centered at each of the xi's, and it's going to have a width that's scaled by this thing called this h, which is essentially the standard deviation of the normal distribution that we're going to be using. So here I've got one little normal distribution centered at one point, and we're just going to put one on every single point, and we're just going to sum them all up. And we get this. This is a kernel density estimate. This is you could think of this as a fancy smooth histogram. If you are a statistician, you call this a PDF or a probability density function. And it gives us an idea of where the data is concentrated. And we can see that it's got these 3 bumps, these 3 local maxima. And it's better than a histogram. It's better than a histogram for a couple reasons. One, we still have to pick the width of our buckets or of our kernel, but we no longer have this problem of being sensitive to where the buckets started, like we did in the histogram. So we've kind of eliminated that problem. Another nice thing about this is that our local maxima are single points, whereas with a histogram, you'd find the tallest bucket, and you don't know where in that range the true maximum value is. It could be anywhere. Here we get an exact single point for each local maxima. But we still have this problem of picking our kernel width, which is kind of analogous to our bucket width in a histogram. We have to pick this h. So here I used an h of 1, but I could have used a larger h and gotten this smoother histogram, or a smoother kernel density estimate, where now we just have two mounds. I could have used a smaller h and gotten a spikier PDF. And this doesn't feel right when you look at this. You don't really believe that this is what your data looks like. You kind of know that a lot of these bumps are just like spurious things that are the result of noise. So what's the right width to use? Well, in this paper, one of the things that they tried is every width. And let's just layer them all on top of each other. So you get something kind of pretty, where here I'm shrinking the h's and I'm just overlaying them. And you get this visualization, which is you could think of as looking at lots of different bucket widths in the histogram world. And this isn't, I mean, it's pretty. I tried to make it pretty. But it's not super useful. Like, one of the issues with it is that your eye is still drawn to those spikes, to the smaller h values, even though they're probably less important. And also bad, your eye gets drawn to what are called the antipodes, like these valleys here where the data isn't. And that's not the answer, that's not the question we're trying to answer. We're not trying to find where the data isn't. We're trying to find where the data is. So they did this. They also did a 3D version where the extra dimension is for the kernel width. So just imagine that this was popping out of the screen and you were able to look down and around at it. Unfortunately, 3D visualizations are generally useless, so they reject that as well. And what they end up with is this thing called the mode tree, which I will show now. Now, mind you, they were doing all of they weren't trying to make a visualization. That wasn't their actual goal. Their actual goal was to come up with an algorithm for finding modes in the data and detecting how many there actually are. And in the process of building that algorithm, they needed tools to understand what it was doing, and they created this visualization along the way. And at the end, they thought it was pretty cool and wrote a paper about it. And that's one of the things that I love about this, is that it's really like a side effect of their thought process in developing like this abstract statistical algorithm. They also put effort into communicating it to people and being just really mindful about how to understand it through visualization, which I thought was really cool. All right, enough gushing about the algorithm. So what we're going to do now is we're going to watch the construction of a mode tree. I'm going to build the mode tree down here underneath the plot. It's just a two-dimensional plot, because that's 2 dimensions is all you need. The x-axis is the same domain as our data. So I've got it going from 0 to 30. And then the y-axis here is the h from the kernel density estimate. It's the width of these normal distributions that we're going to be summing up. And what we're going to plot here is where is the peak of the kernel density estimate. So right now, with the initial width, kernel width of 10, it's going to be around here. So what we're going to do is we're going to slowly shrink h. We're going to slowly shrink those normal distributions that we're summing up. And we're going to follow where is the peak. So it's going to start walking, and we get this line that's moving to the left. And then at some critical width, a new mode appears over here. So what we're going to do now is we're going to trace out where both of those peaks are. And we did a little dotted line here that's connecting them. And we keep going, and then a third mode appears. Now, this third mode appears, and we connect it up to the mode that was the peak of the mound that mode used to be a part of. So we kind of think of this mound here has started to split into 2. I'm sorry, I'm using my hands on my screen like you can see. So we kind of think of that mode as having forked here. And then we just keep going. And we do this until we have a mode at every single point, or until we get bored. All right, so then we end up with this, and this is a mode tree. And what it's doing is it's showing us where the data is concentrated. And in the actual algorithms that they were using when they developed this, they have statistical tests for each of the mode splits to determine whether or not it's significant. So they then go a little wild with the visualization. Here they're showing like the first and third quartiles of each of the mounds as they're moving. I think this one's a bit much. They do it for multidimensional data. This is funny. We all agree that this is funny and useless, but there you go. So yeah, you can generalize the mode tree to multiple dimensions. In a subsequent paper, they do something that I really like, which is they call this the mode forest, where they do the exact same thing that I described before, but for every critical width, what they do is they do bootstrap, where they resample the data, and they're just generating synthetic subsets of the data and seeing what would happen, and then plotting out all the points. Sorry if I'm not doing justice to the bootstrap. I have a whole other talk on the bootstrap. But you get this sense of the confidence in the modes, and where you think that their things might just actually be spurious results. This is a different data set for those of you who are obsessively following along with where the modes are. So that is the mode tree. And happy to talk about it after or answer any questions now. So thanks.
Hello. So it looks like you run into the same problem, though, of having to decide where you're going to stop. What does this get you?
So the mode tree itself doesn't get you everything. Unfortunately, I can't go back. I can only go forward because I rolled my own presentation framework for this. So in one of the, oh, and I went. I went one too far. So there's actual statistics that you can do to evaluate the significance of each of the forks. Each time a new mode appears, there are tests that you can do. So it makes it so that you don't have to have like a subjective decision-making process in the width. And I'm not going to get into the actual test. We can talk about it afterwards. They do all sorts of funky things of like slicing the PDF and then like redistributing the things around each mode in order to do some statistical tests. But that's really what these folks were going after, was automated ways of knowing how many modes there are and where the modes are that are real and not like spurious artifacts of the like noise in your data. Question back there.
Just wondering, did the paper talk about how to read a mode tree? Because like from the CDF, it still makes sense, but once it start going down the tree, it's just like a graph.
No, they don't, and I suspect that it's something that you'd have to learn. Like you'd have to practice, look at a bunch of them. I mean, just like we've learned how to read histograms. We kind of know when little spikes don't matter, and we've got an intuition around it. I've never seen the mode tree implemented in any standard visualization library. Maybe if it were, and it was something that we were looking at constantly, could develop that intuition. I haven't done it, and I've probably looked at more mode trees than almost everybody in the world.
So I'm not a statistician by any means, but I'm wondering, doesn't this visualization, doesn't it maybe obscure some other correlation that's in the data? So like in your case, you know that you synthesized three modes, but you know the real data may have more modes or less modes, and by coming up with this technique to sort of visualize it and use a statistical approach, it may be obscuring the fact that, say not enough data was being collected or something like that.
Yeah, so as far as understanding the modes of your data, I think that this is probably as good as it gets, but all sorts of other properties of your data are completely lost by at least the default visualization that we had, right? Like you don't understand how dispersed the data is. Like you may be able, from the one version that had the quantiles, maybe you can get a sense for like the standard deviation of one of the Gaussians that form in the mixture, but like maybe you'll lose some of the like more esoteric things like the kurtosis and skew and other things that we care about. Some of the more sophisticated ones, though, like the mode forest, do give you a sense, though, of like not having enough data. That would show up very clearly in here. You'd end up with some. It would show up very clearly by not being clear at all. It would just be like a cloud of nonsense, and you would know, all right, no visualization that I have of the modes is really significant based off of the sparsity of my data.
I was curious how you found this paper, or got into mode trees.
Yeah, that's a good question, and yeah, sorry, I probably should have started off with that. So it was. I was inspired by a talk by Isalu Greenberg about benchmarking and all the different ways in which people do things wrong, and started looking at these libraries for benchmarking. There was one I'm a Clojure user, like the core async library that was mentioned before. That's why I was raising my hand. There is a benchmarking library called Criterium in there, where it will run your code multiple times and report back statistics and tries to give you some sense of the significance of your benchmark results. And there's they do not have the feature of detecting whether or not there are multiple modes, but there was a comment in there, hey, maybe we should use kernel density estimates, and that kind of got me started reading the papers about how that works. And there's a mode mode estimation paper by Silverman from like 1981 that was like the precursor to a lot of this work, and yeah, it just went down that rabbit hole. So like the motivating scenario is, let's say you're benchmarking something, and sometimes your code just hits L1 cache, sometimes it hits L2 cache, and sometimes it goes to the network. And you have like these 3 different paths. How are you going to extract that information from a bunch of benchmark timings? And this is one of the paths to doing that.
Have you gone back to try to use this idea on your benchmarking?
I have used some similar things on benchmarking, no mode trees though. Yeah.
Can you online update these? Because like if you have a histogram and you decide the bucket size, like for example, if you're doing benchmarking, you don't need to store all the data points to get a reasonable histogram.
Yeah, that's a good point, or a good
It
question.
doesn't look like this can be, doesn't sound like it can be online updated, but I'm not sure.
Yeah, it's not obvious to me that it can, or that it can be done efficiently, but I'll think about that. That's a good question.
Hi, just wanted to say that I think it's really awesome to talk about even papers that don't necessarily appear to have a use, but I think that, and I'm saying this, I'm not a programmer, I'm more of like a hack things together, but I think you should, an idea is to allow people to input data into something and then make t-shirts out of these. So I would definitely buy some. I think there's one that looks like a water lily with a root, and this one kind of reminds me of the Earth's core temperature, and I think it's really awesome.
All right. Thanks.
I know you can't go back in the presentation, but that one slide where you were showing the value of h walking down and the lines splitting up into more and more lines, is that an iterative process with like a really small step, or is it somehow continuous?
Nope, it's an iterative process. That's the magic behind almost all numerical methods on computers. Unfortunately, don't have symbolic solutions for it. Yeah, I think it's always done. They did it iteratively. I did it iteratively here. Maybe could do it in Mathematica in a nice closed form, symbolic way. All right, thank you.